advanced combustion research. I am Laszlo Kurta, project lead.
I'm Chris Jenkins. I'm one of the engineers in the project.
I'm Lamville. I'm also one of the engineers.
So let's begin by giving a little bit of background about what we're doing. So essentially, small internal combustion engines, 50 cc or less, have a lot of applications around the world. Some being portable power generators, small power equipment such as lawnmowers, and transportation scooters. Unfortunately, very little to no regulation exists on emissions on engines of this scale. They currently produce more than for this reason, they currently produce more than 5% of the total man-made hydrocarbon emissions that contribute to ozone formation. And in some regions of the U.S., lawnmowers using these small engines are responsible for 13% of unburned hydrocarbon emission. One route to alleviate the emissions issue, other than by enforcing regulation or creating regulation, is advanced combustion technology. One form of this technology is called homogeneous charge compression ignition. It aims to essentially decrease the ignition temperature so that NOx cannot form, nitrous oxides won't form, and as a result, lowering emissions. Unfortunately, research in this area is virtually absent, or very little is present for engines of this size. So what our goal is to establish and develop a engine test bed that can be used for testing advanced combustion technology on engines of this size. The way we broke it down, the engine test bed was, there's a structural part, which is the dyno and stand. We have a throttle control, sensor and data acquisition portion, and then the emissions and analyzer analysis. Those are our objectives as well. So we're going to develop a chassis support structure for the scooter dyno system, rewire an instrument engine with sensors, develop a LabVIEW code for the data acquisition, create an automatic throttle control, and then perform EPA emissions analysis, which is the ultimate goal.
Okay, so this is our engine test bed. This is what we were given to work with by the project that was handed to us. We have a 2013 Yamaha Vino Classic scooter. It's a 4-cycle, 50cc displacement scooter with an automatic centrifugal clutch transmission. Pressure ratio is 12:1. All the other stuff you really need. Okay, so this is our budget and our costs for the quarter. We have 3 members on our team, so you're looking at us. So we have $100 per person that's allocated to us. These are our expenses. So we have the scooter stand. So we purchased a stand made out of steel from a manufacturer that will hold the front wheel in place. The battery trickle charger, we're having problems with our battery draining just because the scooter is sitting there. It's also currently inside, so we can't run it inside very well, or at least for very long. So we have a battery trickle charger to keep the battery charged. Fabrication materials for brackets, connections, and connectors and stuff like that for the electrical as well as the mounts. The Arduino servo and servo shield. That was another thing we're controlling our throttle control with an Arduino. We'll get into that more later. A spark plug. We have a custom spark plug produced that houses a port for a pressure transducer, so we get in-cylinder pressure traces, which is very important for our research. And then an EPA emissions analyzer. So we'll have an emissions analyzer. We'll tap in. We'll take readings of chemical emissions from the exhaust pipe. That's our biggest expense, and yeah, it'll cost about $1,400. So.
But as stated there, we currently have an analyzer that we haven't. That's from last year. We haven't tested it out yet. So that's if the current one doesn't work, then we have to purchase.
The project timeline, so far we have the stand complete, and now we're working on sensor and data acquisition. We hopefully will get that done by the end of this quarter, and by the beginning of spring quarter, we hope to get the throttle control all set up and working. Ultimately, by the end of the year, we want to be able to get emissions and diagnostics from the engine, have all that set up and all the DAC set up, and just be able to do EPA tests.
All right, so completed work. So last quarter, fall quarter, is essentially the structural portion. We completed the stand. Essentially, we were first going to do some sort of intricate design. We were going to machine it in-house, but no one on the team at the time had machining capability, so we decided to just purchase a stand, as you see. The stand holds the bike upright, but we're still worried about horizontal motion, so we just use tie downs to tie it down, and it's secured out.
Okay, so this is our current progress. So right now our main focus is the automatic throttle control. So for the automatic throttle control, we need some way that's going, or some sort of feedback system that's going to allow us to run a program for our EPA emission cycle testing, as well as be able to control wheel speed for that cycle testing based on a feedback system. So we have to be able to take sensory input from both the engine as well as the dynamometer and be able to relay that to the Arduino and have the appropriate corrections made. Okay, so this is so for the mounting assembly, I was in charge of the mounting assembly for the servo and the automatic throttle control. Lam was in control of the controls, I guess, for the Arduino. He's in charge of making the program for the Arduino. And Laszlo is in charge of creating the DAC, so the LabVIEW program that's going to read those sensors and that input. Okay, so this is our current progress. This is the automatic throttle control. So you see on the picture on the right is a CAD rendering of what our servo, the bracket, and the adapter will look like. On the left is a picture of the throttle body of the actual scooter. So this bracket right here, these two mount poles are going to mount up to these two holes right here. And this adapter is going to index, this hex adapter is going to index with this nut right here. That controls the throttle body butterflies. They control the air intake into the engine. Those are a couple CAD drawings. On the left bottom is the servo adapter. It's just something that's going to mount to the front of our servos, allow us to index with that throttle body. And the right is the servo bracket. So the bracket is what's going to hold the servo in place over that throttle body.
Oh, for the Arduino, we want two types of controls. One control is want to be able to control the throttle plate through a pot. So we have, I guess, more control. And another is we want the Arduino to do an automatic throttle control, meaning for different EPA tests, it'll hold at this position for a certain amount of time and move it for another position of time, for a set time for different EPA tests. And the DAC, we're just trying to get that set up.
All right, so the next phase is the sensor instrumentation and DAC development. Essentially, in order to do advanced combustion testing, you need certain parameters need to be known within the cylinder. These would be intake pressure, coolant temperature, crank arm position, intake pressure, in-cylinder pressure, air-fuel ratio, and exhaust temperature. We're getting a certain amount of these from the onboard engine control unit, from the feedback from onboard engine control unit. We're getting some of the variables from that. We did need to purchase a pressure transducer for in-cylinder pressure and then an O2 sensor for AFR.
Okay, so this is basically a schematic of our sensory instrumentation and the DAC development. So to be able to provide those EPA tests and stuff like that, it's very integral that we have a feedback loop. So we need to have all those parameters that Laszlo just talked about. We need to have intake temperature, coolant temperature, crank arm position, intake pressure, fuel injector, timing, as well as output and things like that. We need to be able to feed all that into two things, into our DAC. So we need to be able to have a readout on our LabVIEW, as well as have that data feed into our Arduino to be able to make adjustments to our EPA testing cycles and things like that once we get the HCCI set up. Now again, we're just making a test bed for this, so the HCCI stuff will come hopefully next year in the first quarter with Tony, but we need to be able to set up the instrumentation to be able to tap into those sensors on that engine that are already there, as well as adding a couple more. We need to be able to tap into those sensors and take outputs from those and input them into both the DAC as well as the Arduino.
Right now, we're working on basically cylinders. There's the cylinder pressure that's going to measure in-cylinder pressure, and the O2 sensor. The O2 sensor is important in finding air-to-fuel ratio because it'll take the amount of oxygen coming out of the exhaust, and from that we can find the air-to-fuel ratio.
And on the right over there is a picture of what our, it's a schematic of what our spark plug is going to look like. So we have a specially made spark plug that has a channel drilled in it. So if you notice in the left picture is that blue tracing. The thick blue line, that's the pressure transducer. The thin blue line is going to be a connector hose. And then the blue line going through the housing of the spark plug that you can see on the bottom left, that will go directly in cylinder. So that will give us a pressure tap into the cylinder and allow us to do pressure traces while the piston's moving up and down, as well as during combustion. The next one for future work. So as I said, right now we're doing the throttle control with automatic feedback for the dyno. So again, we're setting up that with Arduino, LabVIEW, as well as the sensors on the engine. We're going to do a baseline emissions analysis. So once we have all our instrumentation set up, we're going to do a baseline analysis of the scooter engine. So we're going to run it at idle, different RPM ranges, and hook up our emissions analyzer. Hopefully it works. And be able to get a baseline reading for those emissions. So NOx, unmarine hydrocarbons, everything else like that. As Lam mentioned, our project goal for this quarter, for this year, is by June, by the end of June, by the end of spring quarter, I want to have a method for setting up an autonomous EPA emission cycle testing. So again, that's going to require all three, the scooter, the DAC, and the Arduino setup. So again, the EPA emission cycle testing is going to require all three of those. It's going to be autonomous, so we can send a program into the Arduino and say run it. It will give us the data output into the DAC, and then it'll run the EPA cycle testing for us. And then also we're still researching viable and cost-effective methods for non-spark initiated combustion control. So again, HCCI is one of those, and to do HCCI we need to be able to figure out a way of controlling that in-cylinder pressure, which will ultimately control the in-cylinder auto-ignition temperature, and whether or not we reach it. So we've been researching viable and cost-effective methods for that. We've thought of turbocharging and supercharging, as well as preheating and cooling the intake charge. One of the problems that we're having right now is we are trying to make everything self-contained, so we're trying to make the scooter one unit, so we don't have to have excess units and stuff like that hooked up to it. So it's just we can just roll the scooter, and that's our HCCI bed. And so the problem with that is that nobody makes a supercharger or a turbocharger small enough that will accept a 50cc engine. So we're looking into other methods, including an auxiliary electric blower that will charge the air for us. And then again, mount the in-pressure or in-cylinder pressure transducer with the spark plug. And that's it.